Hello, my name is Akshat Kumar, and I'm a rising senior at the University of Illinois at Chicago, majoring in computer engineering and mathematics. This summer, I worked under Professor Stephanie Miller with PhD student Mustafa Doa Dogan on a project titled Infrared Tags. So we present infrared tags, which are embedded invisible codes in 3D printed objects that can be scanned using infrared cameras, allowing computers and mobile devices to interact with the object. The key idea is to efficiently tackle the scanning and detection of codes, which are invisible to the human eye for real-time applications. In these pictures, we can see some parts of this project about which I'll talk in the following slides. So previous research works have shown that we can embed tags like barcodes and QR codes in 3D objects and retrieve the required information. However, some of the previous research works that we see here are either visible to the human eye, like the layer code, or require large or expensive scanning equipments like the air code. Moreover, some do not support quick detection of the codes and do not allow the use of existing tags and markers. So we came up with the idea of embedding these tags and markers in any 3D printed object using the process which we can see in this slide. So we load both the tag and an object into Rhino 3D CAD software. This tag is then exploded into pixels and is positioned over the object where we want to embed it. Each vertex of each pixel is projected and then they are rejoined to form the code on the surface of the object. To the left, we can see a QR code hovering over a cuboid and each of its pixels embedded into it. The plane on which the tag is gets aligned according to the normals of the object. Finally, after embedding the code, we wrap the object with another mesh, which is basically a shell around the inner object with embedded code. The reason for this is while 3D printing, the inner mesh with code is printed with the regular polylactic acid filament, which is the PLA filament, while the outer layer, which is the shell, is printed with a special PLA filament, which can pass the infrared light. So now the question is why we used infrared light in our research. Basically, the IR light can see through several objects, like you can see on our right. All objects emit light. It's just that the light emitted from most of these objects is not visible to the human eye, because of which we cannot see through them. So we know that hotter objects emit more light, and that light has a higher average energy. Objects at room temperature emit light of relatively low energy. And as we see in the electromagnetic spectrum on our left, that region is called the NIR region. Here is where the IR camera comes in handy, as this light that our eyes can't see can be detected by an IR camera. This is the user interface for the algorithm, which we can see on our right. We developed this algorithm in Grasshopper, which is a software that creates plugins for Rhino 3D CAD software. On our left is the UI panel, which allows the user to load a 3D object and a code to Rhino 3D. The user can then change code's position, orientation, size, and ultimately embed the code in the object. The embedded code's thickness can then be changed manually and also according to the printing filament. Finally, the save feature allows the user to save both the inner mesh with embedded code and the shell separately for 3D printing. So this is the IR camera module with the Raspberry Pi, IR camera, and a power bank, which would read the hidden embedded codes in 3D printed objects. A switch is connected in series with power bank and the Raspberry Pi to allow the user to turn the camera on and off accordingly. Finally, the camera module can also be attached to existing smartphones. So the Raspberry Pi runs a streaming script to stream the output of its IR camera to an IP address. And a device runs a decoding application script that connects to the streaming IP address and runs image processing algorithms to detect an embedded tag. Once the tag is embedded, we can display what tag it is and also display its orientation using X, Y, and Z axes, as we can see with the Aruco wheel at the bottom. One of the advantages is that we can track the angle of either the red or green axis while rotating the wheel, which can help us with some applications such as a car racing game. So since we can track the angle of rotation of the Aruco wheel, as we rotate it counterclockwise, the car moves to the left, and if we rotate it clockwise, the car moves to the right. Another application is allowing users to control appliances remotely, such as a home speaker or a thermostat. When the user points their cell phone at the speaker, it detects the embedded code in it and allows the user to adjust the settings such as volume And when they point at the thermostat, it detects thermostat's code and does the same. Finally, we evaluate our accuracy of our method under different lighting conditions, or when objects were printed with different filaments and with pictures taken from various positions and angles.